Record. All right, it is recording now. And so I'm going to start with this. So last week I talked about ordinary least square, and as I mentioned earlier, it is one of the fundamental concepts in regression modeling. The other important concept in regression modeling is the maximum likelihood estimation. I've already sent an article or PDF for reading on maximum likelihood estimation, and it shows the mathematical calculations, and it has a very good explanation. So what I'm trying to illustrate here is how OLS and maximum likelihood estimation is utilized in regression modeling. So this is sort of the continuation of the regression modeling that we talk about, OLS, that we talked about last week. So in ordinary least square, it is a very simple model that looks at the relationship or the association between X, or the independent variable, and Y, or the dependent variable, and how these two variables are correlated in terms of relationship, and how strong is the relationship, or how predictive is the independent variable to the dependent variable. So this is how a sort of a perfect correlation. So as I mentioned, OLS is simple linear regression, and it's also simple correlations where we can use the Pearson correlation coefficient. And another important then continuation from last week would be that the linear equations that we use for regression modeling is it represents a line. It's a straight line. And in order to make a line, you need 2 points, very simple. So then you can draw a line through these 2 points. And in generalized linear modeling, the independent and dependent variables in the linear equation represent the beta, or the Y, and the alpha coordinates on slide 2. So if you can see here, so your beta is your Y-axis, and then your alpha is your X-axis. And basically what in generalized linear modeling is that your linear equation represent the beta and the alpha coordinates that you see on slide 2. So if we put in all the values for the independent variables, for example, when we are doing multiple linear multivariate analysis or multiple linear regression, it's already recorded. So what happens then is, so your X, or your independent variable, is represented by 1 or 2 or 3, that if you use multiple multivariate analysis. But in simple linear regression, you only have one variable, or x1, and then it tries to calculate the corresponding number for the dependent variable, which is y. So that's your model. In simple linear regression, it's just really one independent variable and one dependent variable, and how predictive is this independent variable towards the dependent variable. So these two numbers show a point on a graph. So basically A and, so that is the direction is you have, in linear equations, you just have 2 points. It's point A and point B. And then that is basically your linear equation represented by a line, and that is the fundamental modeling that is used by generalized linear modeling. If you keep plugging in values for independent variables, so which means that we are now moving forward to multivariate or multiple linear regression, and a dependent variable in a linear equation, you will find that all the points together will make a straight line. So that is the perfect modeling for generalized linear regression. So OLS that we talked about last week is a fundamental concept. And the second fundamental concept that I'd like to really explain here is the maximum likelihood. So what is maximum likelihood estimation? Because last week we talked about OLS which is an ordinary least square represented by blue, which is your best likelihood and bias estimator. So that was the outcome of OLS. So what about maximum likelihood? This is the second most important key developments in statistics due to widespread access to statistical computing. So what's the difference between the two? Because these are the two fundamental mathematical calculations that are being used by generalized linear modeling. So unlike OLS estimation, which is based on set equation, your maximum likelihood estimation is an iterative procedure. So it keeps on repeating itself until it finds that it's already completely maximized. So if the solution and the criterion are farther apart than desired, new values are attempted and new solutions are found. And when the solution is examined and if found lacking, so solution is like the model, it is again adjusted and a third solution is attempted. So you see in OLS, it was just, the product is blue and there is a set parameter for OLS. Whereas in maximum likelihood estimation, it's iterative. It will keep on looking for the best, or what we call the best estimation or the best model for a particular set of data. So it can go to second, third, fourth, until this is the goal of maximum likelihood estimation. It will, at each iteration, it will find and will look at the solution that approaches the goals of the algorithm. So remember that this is a very important concept in maximum likelihood estimation, that it uses an algorithm. So that is, again, another fundamental mathematics that all of us need to already have, because I can't go back anymore what's algorithm again, but that's what maximum likelihood estimation. So there's so many concepts here that are layered that you need. If you don't understand, then just go back again to mathematics, because this is really math. This is math, but I already mentioned from the very beginning that we don't want to talk about and we don't want to discuss mathematics in our class anymore in statistics, because we already have unlimited computing power. The SPSS can already do the math for us. But what do I like all of you to gain is that, remember the four things that I'd always like you to achieve is always look at the relationship of research and statistics, look at the key concepts of the statistics, look at your research question, and then apply those statistics, and then execute the computing component of the statistics. So we're not gonna look at the mathematics. You will never see me talking about this complex mathematics. We will not do that, because that's not how to teach statistics anymore. It's really pointless to talk about the mathematics. But again, just follow me here. The maximum likelihood estimation, or MLE, is that it is very iterative until it finds a solution that approaches the goals of the algorithm. And at some point, the last iteration will be accepted as the final estimation of the effects. And that is what you will get in SPSS output. You will really see that it will have step 1, step 2, step 3, step 4, because it's very iterative. So that is what you're gonna get in regression, okay? And because of how intensive this procedure is, this was not widely used until computer statistical software can do it. So now, regression using generalized linear modeling is now widely used, because you don't need a mathematician anymore to calculate your things in an iterative, your sample, your data in an iterative manner, because the computer can do it for you. So this is one of the major breakthroughs and one of the key development in statistics. And this is one of the reasons why regressions are now becoming very popular. When there was ANOVA was so popular in multivariate analysis, or what we call MANOVA. It was so famous to the point where they created a group of researchers that are called ANOVA researchers. But when the maximum likelihood estimation became programmable in a statistical software, it created another set of researchers called the regression researchers. But as I mentioned earlier, as long as you model your data appropriately, you can really get similar results with ANOVA and regression. And that's why SPSS will actually always give you ANOVA output every time you do a regression analysis, which we will cover tonight. I will demonstrate that to you. So right here, so it's probably quite counterintuitive that why do we say, so here, fast forward right away. So the goal of the maximum likelihood estimation is to find a solution that provides the intercepts and the slopes. So remember that the intercepts and their slopes are your mathematical formula here. For predictor variable, which is your x, so the predictor variable is always the independent variable that maximizes the likelihood of reproducing the individual scores on the dependent variable, which is your y or dv, given their score on their predictor variable. So this is now when you do a multivariate analysis, again, when you have more than one independent variable represented by x1, x2, etc. So in short, the algorithms, so as I mentioned, maximum likelihood estimation uses an algorithm. The algorithms are maximizing the likelihood that we obtain the data. So that's what we get from the sample when we have the data, the observed score, given the model and the parameters being estimated. And what are the parameters again in maximum likelihood? It is the intercepts and the slopes, which I will explain very, very well in a little bit. So just hold on to this concept of intercepts and slopes, okay? Because these are going to be the output on SPSS that you will interpret. So without understanding intercepts and slopes, you will have a hard time interpreting the SPSS output. So let's proceed. So when we say here that the algorithms are maximizing the likelihood that we obtain the data, the observed score, which is the observed scores, given the model and parameters being estimated, and you're going to say, wait a minute, how does that work? Isn't it that don't we already have the data? So what we have are the observed scores on variables for individuals within the population. Now, what we're trying to model is actually that there is really some real dynamic or relationship that exists within the population. So that's what we're trying to model, this relationship, this dynamic. It's a real dynamic or a relationship of the observed score within the population, within our sample. So when we do a research, for example. So the maximum likelihood algorithm attempts to provide a model that maximizes the likelihood of producing the results that we as the researcher have observed or what we have obtained, our data. So what are the differences then between OLS and maximum likelihood estimation? What are their similarities and their differences? Well, in essence, last week we covered OLS. OLS and maximum likelihood estimation are attempting to summarize the observed data to obtain inferences about the nature of the population. And this nature is the dynamic. This nature is the relationship of those variables in our sample that will represent the population. So remember, so in research, we always have a sample. It's impossible for us to do research to the entire population. So we try to, so when we do sampling, we have a sampling frame, and we try to get a sample that will best represent the population that we're trying to really understand. So what OLS and MLE are attempting to do is summarizing the observed data and make some inferences about this relationship. So basically what it tries to do is look at this relationship. Is there a direct correlation? Is there a direct association? Is there a negative relationship? Is there a positive correlation or a negative correlation? So these are the inferences that we're trying to look at the different dynamics or what we call relationship. And then it's important as well that in this modern statistics that we don't only look at linear modeling, that we also look in our data curvilinear, so a curve, it might be a curve, that we also look at cubic, we also look at other potential relationship of the data. And then, so what I will do to illustrate that is when we go to SPSS, I will try to show you the different potential relationship of the independent variable by trying to fit that different line. Is it a straight line? Is it a linear relationship? Is it a curvilinear? Is it a cubic relationship? And you could see, based on the observation, that in our scatter plot, you can see your model is so wrong if you say it's cubic, because the line will show you that that's not what your data represents. What your data represents is a linear. What your data represents is a curvilinear. What your data represents is cubic. So it's so important to examine the different dynamics and the different relationship that exist in the population. But again, we can, in our research, we can never study the entire population. It's so expensive. What we always get is a sample, which is the best representation of the population of interest. So both OLS and MLE examines the dynamics that gave rise to the observed score. So this is really very, very important, because one of the critics of a lot of publications is that we always assume that it's a linear relationship. In the past, we always have our model, we always think that A will result to B and that it is a straight line. But we are now being cautioned that our world is so complex that there could be different representation of that dynamic relationship of the different independent variable that give rise to that gives the predictive power of our independent variable to our dependent variable is sometimes not linear. You could have an independent variable that's only predictive as a linear model in the first 5 years of growth and development, but by the time the subjects are already on their 7th, 8th, and 9th, and 10th year, it becomes a curve. A very good example of that is, what is the relationship of the reading ability of our kids from the time age 0 to the time they're 10 years old? And so we thought that as we get older, the reading ability gets higher, right? But research have shown that that linear relationship, actually, that straight line relationship, that as the older we get, our reading ability and reading comprehension also increases. But actually, it becomes a curvy linear relationship because at a certain age, we do not increase our reading comprehension anymore. See, that's what's so important when we look at our data. So when we look at this different data, we need to look at the different dynamics. We need to look at the different relationship. And we really need to model our data appropriately, because sometimes if we just think that the relationship is linear, then we're gonna miss other relationship that might be represented by our data. So that's one very good example that I can tell you. People always think that, you know, as we get older, that maybe by the time you're 60 years old, your reading comprehension, you can read a whole book and just really understand everything so quickly because you're now 60 years old. Because if you say that there's a linear relationship between age and reading comprehension, but that's not the reality. Science have shown that at a certain point, our reading comprehension actually maximizes, and then the straight line curves, which means that you do not have increased reading comprehension as you get older and older. So very, very interesting facts in life. And so
Doc, when will reading comprehension stop? Or has the point of going to the curvy line?
yeah, very good. So actually, that's one of the data that was presented in the book that's really very interesting to me. And can I send that to you later? But
Ah,
that,
it's okay, Doc. It's okay.
but that is one of the studies that really shows that you have a straight line, which is the higher, you know, the higher the age, and then you will have higher reading comprehension. But then at a certain age, that comprehension starts to go down. So it's no longer a linear relationship, but it's a linear to a curvy linear relationship of the data. So very, very interesting. All right, so OLS and MLE, what's the difference? Well, they use different mathematical techniques to get to the same goal. And the goal is always to examine the dynamics. They always, but on OLS, there was a very specific math, right? You are boxed in. This is your formula for OLS. Whereas in maximum likelihood estimation, there is iteration, which I will demonstrate to you in the next hour for sure. So what is the conceptual explanation of maximum likelihood estimation? Because as I promised you guys, we're going to really discuss concepts here, because that's the key for modern statistics, is to understand the concepts. So the conceptual explanation of maximum likelihood is that in regression modeling, so regression is line. Remember that regression always think of line when we talk about regression. So in regret is to fit a line. So in regression modeling, the intercept, which is often labeled, we don't understand why SPSS labeled it as constant. So this is another thing, because we're going to start interpreting regression tonight. We're gonna do actual regression tonight on SPSS. So remember that the intercept, which is labeled as constant by SPSS, which is weird. SPSS should just call it intercept. I don't understand why they change it. But in regression modeling, the intercept, which is labeled by SPSS as constant, is the expected mean value of the dependent variable, or your y, when the independent variable is 0. So I will explain this to you again back later on, but hold on to this very important concept of MLE. So for example, if your independent variable is IQ, and your dependent variable, which is going to be the example that I'm going to show you on SPSS, and your dependent variable is the NCEE score, because I simulated this. I spent 6 hours today just to simulate this on my SPSS, which is really, really cool. So what happens here is that in regression modeling, the intercept is the expected mean value. So that's mean score, because it's parametric again. So mean value of, for example, your NCEE score when your IQ is equivalent to 0. So remember this, because we will look at this on the output. So this is, in regression modeling, the intercept, or the constant, is the expected mean value of dependent variable when the independent variable is 0. So think that if your dependent variable is NCEE score, the mean value of NCEE, for example, in my simulation was 29, the independent variable, which is the IQ, is 0. So in my modeling, in my simulation for NCEE as a dependent variable, the NCEE score, National Collegiate Entrance Exam, when I model it that my mean score of my NCEE was at 29, my independent variable, which is the IQ, was 0. So that's what we're going to look at on SPSS output tonight. The slope indicates the steepness of a line, and the intercept indicates the location where it intersects an axis. So remember, you have your y and your x-axis. So your slope is where, how steep does the line keeps going down. So that's the slope. So if we look at here, from here, how does this line keeps going down is what we call the slope. And then the intercept is, where does this line settle when we're considering the alpha and the beta, or what we call your dependent and your independent variable data. So this will all be demonstrated on our output, on our SPSS simulation of the NCEE and the IQ score. So the greater the magnitude of the slope, the steeper the line, and the greater the rate of change, right? So when our dependent and independent variable are so, the variance is so big, the magnitude of the slope, then the steeper and the greater is the rate of change of the slope. Maximum likelihood estimation is trying to estimate the various parameters all the time, which is the slopes and the intercepts, that best model, or the ability to recreate the observed data. Maximum likelihood will repeatedly attempt estimation based on a slightly different coefficients until it fits the observed data as good as it can be. And what does that mean? What that literally means is that there's an algorithm in maximum likelihood estimation, as I've mentioned. It uses an algorithm. And the algorithm in maximum likelihood estimation is that unless the change is greater than 0.001, it will keep on finding another solution. So right here, when the observed data is as good as it can be, what it means is that the iterations fail to improve the fit by an appreciable amount, such as less than 0.001 change. And I'll show this again to you on SPSS. It will really, it will tell you that the iterations, such as your step 1, step 2, step 3, step 4 of regressions, will stop when the change when the change of the next iteration is no longer greater than 0.001, because that's the algorithm of the maximum likelihood estimation. So let's go to, these are my first slide set. So let's go to quickly SPSS now. So I've explained OLS and I have explained maximum likelihood estimation. Let me do SPSS to demonstrate these things before I will go to logistic regression, because logistic regression is binary, which means the dependent variable is binary, and it uses chi-square and the odds ratio. That's why it's very, very appealing to a lot of researchers and very appealing to a lot of epidemiologists, so logistic regression. But I've covered so far OLS, simple regression, simple linear regression, which is equivalent to simple correlations, such as your Pearson's R. They're all related. And now let me demonstrate that to you on SPSS. So right here is the, so I simulated this. We're gonna look at NCEE and we're gonna look at IQ. So NCEE is our dependent variable and IQ is our independent variable. What we're trying to find out is that how predictive is the IQ? How predictive is the IQ of the student in getting a higher score to NCEE? So now let's go to analyze, and we're gonna go to correlation first, right? And we do bivariate, and I have NCEE and the IQ score. And here's our SPSS output. It tells you that the Pearson correlation of NCEE with IQ is 0.221, and that it is statistically correlated. It's a positive correlation because it's not, there's no negative sign, but it's a weak correlation because it's only 0.221. But it's statistically significant nonetheless because it's 0.03. It's less than 0.05. So that's our first. We already know that this is correlated. So let's find out then if we put a regression, because regression modeling can give you additional information than a simple correlation. So now let's do regression. Let's do linear. And we will put NCEE as the dependent variable. And we will put our IQ as independent variable, or our predictor variable. And here is the statistics. Aside from the automatically SPSS will already give you the model fit, the estimates, but what I added here is the confidence interval, because I always love to see the confidence interval. Somebody needs to mute their microphone because it gives a lot of echo, please. The confidence interval, I always include it. And I also like to include descriptives. And then we press just continue. And for the plots, what I'd like to do, I have 5 minutes more. It's 8:35. I think I started at 8 or maybe 3 minutes. We also need to do the Z of the predictive variable. So we need to have this because one of the assumptions of regression that I talked to you is homoscedasticity or heteroscedasticity, which is equivalent to the homogeneity of the variance in ANOVA. But we need to do this in regression because this is the way how we know whether the assumption of regressions are met. Just like ANOVA, it has assumption. Regression also has assumption. And so we're going to look at the Z predictive regression plots, and we'll put that in the X because that's our predictor variable or our independent variable. And then we need to put the Z residual, which is the residual of our dependent variable, in the Y. And then we press, and then you also need to check histogram, and you also need to check normal probability plot. And then we press continue. And by the way, once I cut off, I will press the next time slot, okay? Because I need to continue with this in very, like in an hour. I need to finish this in a continuous manner. So if our lines are cut, go right away to the second time slot that I emailed this morning. And then we don't need to say this save option here. This is really for very fancy. If you still want to do unstandardized, standardized, studentized, deleted, or studentized, deleted, these are very fancy. We don't need to do that. We could just use our very basic plots to check for homoscedasticity and heteroscedasticity, which are very important part of our assumption for regression modeling. And here for the different option, we always put our 0.05 for our F statistics, which is for ANOVA. You know that ANOVA uses F statistics, and t-tests, you have your T statistics. And then these are already, you don't even need to click this part because SPSS is already a default setting. And then we press OK. And this is what we're getting. So now this is the meat of the lecture, is the regression, okay? So this is our regression, simple regression. So first we check our descriptive statistics, and we look at the mean score of our NCE is 30 with a standard deviation of 3.8. Our IQ score, and remember I simulated this, so this is fictitious, okay? But I modeled this to really demonstrate regression and the maximum likelihood estimation. And here you will also find out that in your regression output on SPSS, you also have the correlation. So back again, it's 0.221. That's the same thing that we get when we did the correlation coefficient. And why did I use a Pearson correlation? Because I know I already checked my my data that it is normally distributed, which again, we will also check in regression analysis. And then, as you can see here, the correlation, the significance is 0.01, which is slightly lower because what we got when we do the Pearson correlation, it was 0.03, correct? So that's an output that you see in regression. The second output is the variables entered when entered or removed. This is not applicable right now because this is only for when you do multivariate or multi-regression. Because right now we're only doing simple regression, so that's why that's blank. So ignore that, but it will always give you that output when you do regression. Here, the model summary, what this means is that the R value is 0.221 and the R square is 0.049. What does this mean? Remember that the R square is how much does the independent variable account for the result on the dependent variable. So it only accounts 4.9%. Because the R-square is the shared variance between the two variables, your independent and your dependent variable. So what it tells you is that it's really quite, this is not surprising though, because remember that this is only 0.221 positive correlation. So the relationship is not really, if this would have been 0.8, and remember I simulated this. So I intentionally simulated it where the correlation is weak and that the R-square is obviously going to be small. It's only 0.049, which means 4.9%. It only 4.9% is only is what it accounts for in terms of the shared variance between the independent variable and the dependent variable. Your adjusted R-squared is 3.8%. That's slightly lower than your R-square. That's because the N, or the sample size here that I plug in, is 88. The difference between the R-square and the adjusted R-square is going to be huge if you have a very small sample. And basically what the premise of this adjusted R-square is that if you have only an N of 2, you will have a perfect correlation, right? 1 and 1, because you only have 2. You only have an N of 2. So basically, this adjusted R-squared is going to be really small, and the difference between the two if you have a higher N sample. And then the standard error of the estimate here is actually very good. It's only 3.78. That's the error, the standard error of the estimate. And again, this is a function of the model. This is a model summary. This standard error of the estimate, which is only 3.78, is